So now let's look at next chapter, which is the scanning probe, microscopy, and lithography. Yeah. So before before talk about lithography, so first of all, we want to talk about the microscopy. That is the imaging. So for the imaging, we have to compare it with the ICM. For the vertical direction, for the Z direction, AFM or HTM, they are a lot more accurate than ICM, because for the ICM, normally we have the top view. If we want to see the cross section, we have to cut the wafer and tilt the wafer. Then the height information will not be very accurate. It's about a few nanometers. For the AFM, we can get better than 1 angstrom resolution. For the lateral dimension, scanning probe microscopy is also more accurate than ICM, but this is only good when we have the flat sample. When the sample is not flat, this is not good. That's why in reality, so people use ICM a lot more than the AFM, because the sample may not be flat, then the image will be artifact, will not be real. For instance, if we have a trench here, if we have a trench, this is the trench. When you do the imaging on the AFM, the tip, so the tip may be slack by the corners. As a result, so when you see the image will be something like this. You will see a trench, this kind of shape, but this is the artifact. So because of this very serious artifact, the AFM is not as popular as ICM, but this depends a lot on the tip. If we have very high aspect ratio tip, then the artifact will be smaller. But normally the tip is the pyramid shaped, so you have this artifact. For the AFM, so we do not need a vacuum, and we can even do the imaging in the liquid. We can even do the imaging in the liquid, and we do not need the sample surface to be conducting, so we can image insulating material. As a result, this is also very popular for the imaging of the biological materials. Very important for the biological materials, by the imaging in the liquid. And also, AFM is much cheaper than the ICM, because for the AFM, we do not need no high vacuum, no high voltage. You can buy an AFM at about maybe $20,000. But if you buy the ICM, it's about, normally it is $500,000. So the first HPM, so the first scanning probe microscopy is actually HTM, scanning tunneling microscope. This one was invented by those two persons in 1981. They won the Nobel Prize in 1986. But later on, the AFM was invented in 1986. This is the first HTM. It's something like this. So the key is how to move the sample precisely. So we need to have the, in order to have the atomic resolution, we need to move the sample precisely. So this is realized by the piezoelectric material. This is piezo, this is also piezo. So we have the piezoelectric material. This can control the movement at a very, very high precision. So we know that this is not the first time that human beings see the atom structure. So in 1951, people used the field. If you remember this one, this is the field ion microscope. A field ion microscope. So when we talk about helium ion beam, we talk about field ion microscope. This one can also see the atomic structure, and this is done in 1951. But this one can see the sample on the surface. You know the distance between the two atoms. This one you just see the arrangement of the atom on the surface. You do not know the distance. For the tunneling, this is the scanning tunneling microscope. This is a simple principle of the tunneling process. On the left side, so we have this plane wave. This is like a plane wave. On the right side is also a plane wave. Inside the tunnel barrier, this is the barrier. Inside the barrier, so we have this exponential decay the wave. So for the plane wave, for the kinetic of the light, we know the plane wave is something like this. This for the kinetic of light. But this term is the time, for this one, we can ignore this one. For this K, the K is given by 2 pi over lambda. So this for the light. This is K for the light. So here we have, this is also, for the electron is also similar. This term here. This term is also like exponential term. So what is this k here for the case of the electron? So k we know equal to 2 pi over lambda. So 2 pi over lambda. So lambda equal to 2 pi over, if you remember, h over p, right? Lambda equals to h over p. H is Planck constant. P is the momentum. So P equal to, there's the momentum. Energy given by, we know about those things, right? So this is the momentum, this is energy. As a result, you get something, this one is given by, so this one is h over 2 pi, h over 2 pi is h bar. So they have this one term. Something like this. So this is the K. This is the K. This is the in the free space. This is also in the free space, but they have some decay. This K prime is smaller. It's smaller. So inside the tunnel barrier, the formula is similar. It's also something like this. But the difference, there is some difference. The difference here. So inside this one we have here, we put the term E. So inside the E become, so the E become E minus V. V is the potential barrier. E minus V. So because you see here, the potential barrier is higher than E. So this one is a negative number. You get this one is negative number equal to I become this one, right? So because this V minus E, this is a positive number. So that's why you have this inside. You have this. You have one I here, another I is here. So I square equals to minus 1. So here you have this. So here you have this minus 1 term. Because you have one I, another I, you get minus 1 term. Then inside you have this V minus E term. You have this V minus E term. And then still you have this 2m term. So this is the tunneling, basic principle of the tunneling. So why you get very high resolution using scanning tunneling microscope? Because even though the tape may not be sharp, if you look at the tape, it may be something like this. It's kind of blunt. But because by chance, some point will be protruded. For example, the tape can be, something like this. So there is one item. This item is protruded. So this protruded item, that is higher than the other one. This one take about 90% of the signal. You see here, 90% of the signal. So effectively, this single item takes most of the signal. That's why you get this atomic resolution. Even though the tape may look like blunt, but actually there is always one item that is more protruded. Touch the surface first. And now we look at AFM, atomic force microscope. So this one detects the force. There is the long-range force and the short-range force. For the long-range force is the electrostatic force. This is the Coulomb force. This is Coulomb force. Something like this. Coulomb force. Magnetic force is similar to this curve, similar to this one. And double layer electrostatic force. This is happened in a liquid. This is the long-range force. For the short-range force, we have this 1 watt force, about 10 nanometer. Surface-induced solvent ordering. This is not so clear. 5 nanometer. Hydrogen bond, 0.2 nanometer. Contact. So we know that for the case of 1 watt force, this is normally it is the attractive force. This is because of the induced dipole. At any moment, if you have one atom here, you have another atom here. For example, at this moment, the charge, the electron is at this position. Then because of the Coulomb force, the other charge will be something like this. So that means there is the induced dipole. So this dipole here, this dipole induced dipole. So this dipole here is induced by this momentarily charge. But this one, at another time, that the E may come to here. Then this E is also induced to the other side. So we have this dipole interaction. This is the 1 watt force. This is attractive force. So how to do the detection? Here is the setup. So you have the cantilever. You shine the laser beam, and you divide the photodiode into 4 parts. And when the cantilever is bended, then it will go to different places on the photodetector. on the photodiode. This is very sensitive. A little bit change of the height, a little bit change of the bending, it will change the optical position a lot. This is very accurate. The accuracy for this is called optical. There's a name for it. It's called optical lever. The cantilever. This is a cantilever. This is also called optical lever. So a tiny change can be detected. So the accuracy is much better than 1 angstrom. So this is very accurate. So the problem is that this is bulky. You need laser beam, you need a photodetector, and this is bulky. If you want to have a large array of the AFM cantilever, then this will not work. Then, as we will see later on, there's the deflection. The deflection can also be detected by the piezoelectric material. You put some piezoelectric circuit on the backside, then this can also be used to detect the bending. Then you can have many tapes at the same time. But we have this kind of standard laser beam optical component. This is bulky. You cannot make so many of them. So for the normal detection of the Z direction, the beam spot side will move up and down. Will move up and down. So you measure the A plus B minus C, measure this value. This for the normal bending along this direction. If you move the tape lateral direction, the tape will be twisted. So the cantilever will be twisted. Then you see the laser beam move left and right. This is used for the lateral force of friction microscopy. So we have you drag laterally to measure the friction, lateral force. So for the operation, so you maintain the same signal. When you maintain the same signal, that means you maintain the same degree of the bending. When you maintain the same degree of the bending, so you move the tape up and down to maintain the same degree of the bending. But this movement, up and down movement, this is equivalent to the topography of the sample. This is the first curve. So far away, no force, and then you have this 1 volt attractive force. And when you touch the surface, it becomes a repulsive force. So this is, you see 1 to 2. Then you have a jump. There is a small jump because at this moment, the 1 volt force can overcome the cantilever bending force. Small jump. Then you have this contact. But when you retract, you can see the first curve come here. But you need to move to this point. Then suddenly get released. So what's called this point 5 here? But this is because when you do the AFM in the vacuum, the forward and back, they pretty much overlap. But when you do this one in air, there is the capillary force. You need to pull the tape out of the capillary force, out of the liquid. That's why you have this one here. If you have the contamination, you can even have more complicated. So why we have this liquid on the tape? Well, because I think you have learned, you have taken many of you take a surface and interface. If you have something like this, a structure like this, so which part is easier to get this water condensation? If you have learned surface interface, you see that this part easily gets water condensation. But those part here, no water condensation on those part. But there's some water condensation at this part. So we have the AFM probe. This is AFM probe. There is also water condensation here and water condensation here. That's why this will happen. But when the humidity is bigger than 20%, humidity in the air bigger than 20%, you will get this water condensation. Effectively, the tape always touch into the water. A very small amount of the water. And now we look at AFM tape and its fabrication. There are 2 ways to fabricate the tape. The first one is the etching. We can do the etch the tape. The second one is called a molding. This one is mold. You make the mold, then you mold it. So here we will first talk about this example. There are many different ways for the tape fabrication. This example is just one of them. So for the commercial production, you don't have to use this method for the commercial production. I will show you later on the fabrication steps for the commercial production. But first, we use the SOI wafer. SOI, what is SOI? It's called silicon on insulator. Silicon on insulator. Here we have the silicon on the top. Silicon on the top. The green color is the insulator. We have silicon on insulator. First, you're passing an oxide mask. You etch a little bit dry edge, but this step can be skipped. Then you do the wet edge. You do the wet edge. Then you pattern the oxide mask. You pattern another oxide mask. Then you etch away to define this. This is the cantilever. This is the cantilever part. Then you pattern the oxide from the backside. You pattern the oxide mask on the backside. Then you QH etch the silicon. You QH silicon. This part one here. This is the 111 plane. This is the 111. This tapered plane here is the 111 plane. But here they use the oxide as the mask. But actually we know that oxide is not a very good mask for the QH etching. The best mask material for the QH etching is the nitrate. Silicon nitrate. Silicon nitrate is a much better etching mask for the QH. Then you use BHF to remove the oxide. Then dry etch away this residual silicon layer. Then remove this green color oxide. You have this freestanding AFM tips. This is the etching method. So for the molding method, first you make this inverse pyramid shapes this hole. So this one here, the side wall here, this is the 111 plane. But this one here, the side wall here, this is not 111. It can be, for example, it can be a 331 plane. So it's complicated. We have this is undercut the mold, undercut the mask. This can be 331 or 441, complicated. But we have this kind of etching. If this is one, it's always a 111. Then you coat a silicon nitrate. This layer here is the silicon nitrate. Then you put the handle part. Then you remove the bulk silicon. You get this tip. So the advantage for this tip is that the most advantage, the cantilever here, this cantilever here is determined by the film thickness. For example, if you deposit 600 nanometer. If you deposit 600 nanometer silicon nitride using low pressure chemical vapor deposition (LPCVD), then the cantilever thickness will be 600 nanometer. It's well defined. But in this one, the cantilever thickness here is defined by this etching process. So even though the etching may be accurate, but the starting wafer, the SOI wafer here is not accurate. For instance, if you bag a SOI wafer with the 10 okay, sorry. If this one, you want the top silicon layer to be, this is what you want. You want 10 micrometer thick with the top silicon layer. But in reality, you never get 10 micrometer. You get 10 plus minus 0.5 micron. You can see this is very accurate. It's very inaccurate. If you etch away, if you etch the silicon, you leave behind 3 micrometer. If this is 3 micrometer left behind, then it will become 3 minus plus minus 0.5 micrometer. It's very inaccurate. But in this case, the cantilever thickness is determined by the film thickness. It's very well controlled. That's why you can get very thin cantilever. If we have very thin cantilever, you get very small force constant. You got very small spring constant. If we have very small spring constant, this is good for the contact mode. For the contact mode measurement, we need a small force, otherwise the sample will be damaged. We need small force. And also, if you want to measure soft material like the biological material, you also need very, very soft cantilever. This is done by the silicon nitride. For the silicon nitride, the tip shape is the pyramid, and usually it is like this kind of triangular shape to prevent the twist, to prevent the twisting of the very thin cantilever. So now I will show you the fabrication procedure by the nanowort. Actually, I have already uploaded the slide. You do not need to remember the fabrication process, but you know it's good to know if you are interested. So you can see this slide. You can see this slide in the Learn. You can download this slide in the Learn. This is the wafer of the tips. This is 4-inch wafer give you about 400 tips. 6-inch wafer give you about 1,000 tips. This is the tip. You use the tweezer to take the tip out. So this is the tip dimension, the side view. This is the fabrication procedure. This one is the etching process. Etching process, you can see. You can see the details later on. This is etching process. So the second one, this is the molding process. This is the silicon nitride molding process. You can see here. They make this inverse pyramid shape the cavity. Then you coat the silicon nitride onto it. You coat the silicon nitride. Then you put this handle layer of paraglass in the handle. Then finally get the tip. You can take a careful look afterwards. So now let's look at the typing mode AFM. So usually there are two types of the mode. One is the contact mode. This one is the most straightforward. You drag the tip along the surface. The problem, you have very large friction and also you have very large damage. You can see here because it drag on the surface. To solve this problem, we use the typing mode. This typing mode is invented in the late 1980s. Typing mode. In this case, the tip tap the surface. It will touch the surface only at a very small fraction of the time, maybe 1% of the time it touches the surface. Most of the other time is not touching the surface. This is called a typing mode. So typing modes give you smaller friction. This is good for the soft material and also it will not damage the sample. So in between we have this non-contact mode. But in reality, this is what you can buy the non-contact mode AFM. But in reality, this never works well. It only works. We have the humidity. If the humidity of the environment is less than 20%, this will work. Otherwise, if the humidity is high, you have always some water. Get the water. The tip. They have some water condensation. We have this water condensation. You cannot maintain 1 nanometer. You cannot maintain 1 nanometer distance. Effectively, you will touch that. You cannot maintain this 1 nanometer distance. Effectively, you touch the sample. So again, this one is available but not popular. It only works when the humidity is low. And now let's look at the typing mode. So in the typing mode, we have this free space. We have this free amplitude. You have high amplitude. When the tip fills the sample surface, you get this reduced amplitude. So in the measurement, you maintain this amplitude to maintain a certain distance from the sample. This way, you can get the topography information over the sample. So we can not only measure the amplitude, we can also measure the phase. The phase measurement. For the phase measurement, this is the phase. We measure the phase lag. You can see this is the drive signal. So what do? We drag. We have at the handle part of the cantilever. We vibrate. This is we do the vibration. This is the drag signal. Then this is the cantilever signal. You can see this signal lag behind the drag signal. How much is the lag amount? This determines whether the sample is soft or hard. For the soft material, there will be more lag. For the hard material, there will be less phase lag. This way, you can tell the hardness of the material, the Young's modulus of the material. For the AFM, we know that it can operate in a liquid. It's good for the biological imaging, such as the cell, chromosome, a protein, and DNA. Now let's look at other forms of AFM. The first one is the lateral force microscope. So we drag the tip along the perpendicular to the cantilever direction. Then the cantilever will be twisted. And when it is twisted, you can see this is the forward scan, this is backward scan. You have the topography information, but you also have the twist information. So how much is this? How much is the twisting? Depends on the friction, depends on the surface energy of the sample. That's why it's called friction force microscopy. You can see here, this is the normal AFM image, topography image. This one is the lateral force microscope, lateral force mode. In this case, this is the material is the PET film. So there are lots of particles. Those particles here is the silicate, filler. From this image, you can see the filler material has higher friction than the PET material. So on the right side is the lateral flash microscope of the self-assembled monolayer. So here we have two self-assembled monolayers, this one and this one. This is done by the micro contact printing. So this one you can see, this one has higher friction force than this one. So the next mode is the lift mode. So we know that for the force we have different ranges. Different force has different ranges. You can see it here. So this is the long range force, this is the short range force. If we want to detect magnetic force or electrostatic force, those are long range force. But if the tip is too close, to the sample surface, it can also feel those short range force. In order to avoid those short range force and measure only the long range force, so we do the lift mode. We do this lift mode. So there are two paths. So for the first pass, so we follow the sample surface. We get the topography information. Then we do the second pass. This second pass, we lift a certain distance. So we do this measurement. The lift height is about 30 to 100 nanometer, but at least it should be more than 10 nanometer. When it is more than 10 nanometer, you can avoid the van der Waals force. But when you're in the lift mode, we no longer feel the van der Waals force and the contact force. What we feel is the non-contact force. So those force including magnetic force or electrical forces. So those forces will show up when you lift the tip 30 to 100 nanometer away from the sample surface. So the first application for this one is the MFM. It's called magnetic force microscope. So the idea is simple. So you coat the tip with the magnetic material, then you can do the MFM. But you need the accessory. You need some accessory. You cannot do the MFM using a simple AFM. So this is the setup. You can see. So first we do the first scan to give you this topography information. Then we follow the surface again. We do the second scan. We get this magnetic information. And this corresponds to the switching. This is the domain wall, the wall of the domain. To map magnetic field or magnetic domain. Earlier time, so people use this kind of, it's called a Bether pattern. This Francis Bether. So use the Bether pattern. So you use some magnetic nanoparticles, for example, iron. This is magnetic nanoparticles, but the nanoparticle may be elongated. Nanoneedles, elongated magnetic nanoparticles. Then you put along the magnet, you shake it. So then you can see the elongation, the arrangement of the magnetic nanoparticles can tell you the magnetic field orientation. But this one, the resolution is low, maybe 10 micrometer resolution. To get to very high resolution, so people use MFM. You can use MFM. So this is the MFM image. This is the this is the topography image. This is MFM image. For the MFM image, so we measure the force. We measure the field, magnetic field. We measure magnetic field gradient. So we know that the force constant. So we have this one. This is the force. Then the change of the K equal to the K equals this value, dF over dz. So dF over dz over K. This is from the magnetic force. Then the total K will be K effective K value equal to K0 minus dF over dz. This dF over dz is the K, the change of the K induced by the magnetic field. So we know that the resonant frequency F the resonant frequency. We have the change of the spring constant. You got the change of the frequency. So you can detect the change. You can detect the change of the resonant frequency. But in reality, we do not detect the change of the resonant frequency. We detect the change of the phase change. So the phase change corresponds is correlated to the frequency change. So now I look back again this term, dF over dz. So what is the magnetic force? So for the magnetic tip, so what do you do here? So you have the magnetic tip. This is the tip. Then you coat a layer of the magnetic materials. For example, you can coat a layer of the cobalt. You can coat, this is the cobalt. If you coat some cobalt or nickel, you coat the material cobalt and nickel, those are magnetic materials. Then you have this sample. So for the nickel, you have the pole. You have the magnetic pole. This pole. So this is the positive pole, negative pole. So this is what you can see. This is what you can consider as the north pole. This is the south pole. We know that for the magnet. For the magnet, so we have the north. Sorry, this should be negative here. We have the north and the south. The south, this is the magnet. So you can see this one. We have this north pole here. Then the force will be given by. This is the magnetic charge. But actually we do not have the single pole for the magnetic. But here we can assume we have this magnetic charge. So the force given by magnetic charge times the magnetic field. So because we have seen that we detect this term dF over dz, we detect dF over dz. As a result, what do we detect? We will detect a dB over dz because force given by this one, dB over dz. That means we detect the gradient of the magnetic field. Now this will happen as this will be large as the boundary of the two domains. So what's the other ways to do the magnetic measurement? Another way to do the magnetic measurement is using the Lorentz force. This is called a Lorentz force microscope. I will show you a Lorentz force microscope. So here is the Lorentz force microscopy. So this can also be used to detect magnetic domain. This is done in the TM imaging. This is the transmission electron microscope. The TM imaging, you can do the Lorentz detection. This can also tell you the domain orientation. You can see when the domain is this way, electron deflected this way. When the domain this direction, electron is deflected to the right direction. This one can be detected. This way you can get some magnetic domain information of the material. But for this one, you need the sample to be very, very thin, to be less than 100 nanometer. So we have this very thin, then the magnetic information actually will be affected. That means when you prepare the sample, we prepare the TM sample, the magnetic domain is already altered. This is not as good as MFM. MFM can measure any sample, but this one give you higher resolution of the magnetic information than MFM. So the last one is we can do similar to the MFM. We can also do the electrostatic force microscopy. Electrostatic force microscopy. So in this case, we do not use ferroelectric material. But here we use those material is the ferromagnetic material. But here we do not use ferroelectric material because we apply the bias. We have the bias voltage. The charge will be induced. So this charge will come out by itself, induce the charge. So we do not need. As a result, we don't need ferromagnetic material. But this also gives you the trouble. Because the charge can be induced, so you do not know, it's hard to know whether the charge comes from the sample or the charge comes from the mirror charge. For instance, we have this positive charge here. It will induce some negative charge. This negative charge is called a mirror charge. Mirror. This is a mirror charge. This charge is because of the positive charge on the tip. So then you need to figure out a way to distinguish whether this charge is the mirror charge or this charge is from the sample itself. So this makes it more complicated to extract useful information from the image. Now, this is example of the EFM. This is called electron force microscope mapping. This is the mapping of the surface charge. You can also map when the device is turned on or off. When the device is turned on or off, you can also see the difference. And this is called a voltage probing. So you can do many different forms of the electrical measurement using AFM. If you want to know more, you can read this book. It's called Electrical AFM for the nano electronics. You can also make the contact. If you make the tip to the contact, you can measure the current. You put the ampere meter here, you can measure the current. So when you measure the current, you touch the tip, you touch the surface, you measure the current. This is why you can measure the resistance. This called something called spread resistance measurement. You measure the resistivity of different part of the material. You can also measure the work function. You can also measure the work function of the material. This is called a Kelvin force microscopy. Similar to this one, you measure the work function of the material. This is also a kind of electrical measurement of the material. So I forgot one thing, so I can show you one more thing before we stop. So here we talk about a constant mode, non-constant mode, and vibration and typing mode. Actually, in the recent years, there is another mode. There is another mode that's also become more and more popular. It's called a peak. Called a peak force mode. Peak force mode. So this is called a peak force. This is also a typing mode. The difference from this typing mode is that for this typing mode, the vibration is the same as the resonant frequency, which is typically hundreds of kilohertz. So for this peak force typing mode, so the vibration is about 2 kilohertz. So this one is much smaller than for example, 300 kilohertz. 300 kilohertz. So it is still a typing mode, but the typing frequency is much lower than the resonant frequency. I can show you more from the internet. So this is the peak. This shows the principle of this peak force typing operation. Peak force typing operation. So you can see here, this is the force. So effectively, you pour the surface. Then you have this curve. This is the first curve. This is the first curve as we have seen. Then you withdraw. You got another first curve. The force from the maximum force here. The maximum force here. This is the peak force. But this peak force is controlled. It's well controlled. This way, you make sure that you will not touch the sample too hard. This is good for measuring the soft material and also measuring in the liquid. So effectively, you do the force measurement at every of the pixels. That means you do this kind of force measurement at all of the pixels. This way you can control the force. So you will not damage the sample. Thank you.